Okay, so looking at the power rule, first of all, I did put a sheet called the Power Rule Exploration Sheet. I named it, I think it was 321A. And I put the answers in there because I don't want you to spend a lot of time exploring or expanding it using the limit definition of derivatives. But if you take a look, go and look at that right now and see if you can come up with a rule based on the work that's there. Unless you've done it already, that's even better. And then come back. Pause the video now and come back. Write in your rule here. And then we have the general binomial expansion. This is from the do now. So some of the things I want you to notice. First of all, the power here is n. I know that the first term is going to be x to the nth power, where the leading coefficient was 1 here. And the power for x is n, and technically delta x is to the 0 power. We don't write that because that's also equal to 1. Then the next term, we have 1 less x, so it's going to be x to the n minus 1, but 1 more delta x, so that gives us delta x to the first power. But what we talked about in the Pascal's triangle was that the leading coefficient, or not the leading coefficient, but the coefficient for the second term is always going to match the power that I'm expanding at. And if you go look at the last term, they're similar. The last term is going to be delta x to the nth power, so whatever the power was that we're expanding at. And the coefficient to the second to last term is n. And we have 1 less delta x than the last term with 1x. So you descend the x's power and you ascend the delta x powers for each term. When you look at the middle pieces here, these coefficients, this is n choose 2, n choose n minus 2. At the end of the day, for our purposes here, it doesn't matter exactly what those values are. So they're just going to be some constant, like k sub 3. This could be k sub n minus 3, for example. Just any constant, any real number constant that we end up with there in those middle terms in there. If you look at the power rule then, if n is a rational number, then the function f of x is equal to x to the n power is differentiable following this rule. So I'm hoping that you figured that out, that you take the power that x is raised to and move down as the coefficient, and then you subtract 1 from the exponent. Now there is a couple of one unique situation down here. For f to be differentiable at x is equal to 0, n must be a number such that x to the n minus 1 is defined on the interval containing 0. We'll learn how to deal with that if something different happens. Some things also I put it here, but I'm going to mention that again later on, that dx is an operation, just like if you take sine of x is an operation. You can't do sine of x is not the same x sine like that. That makes no sense. You have to take sine of something. Well, the same goes for d dx. You can't do d dx of, let's say, x to the n. That's not equivalent to x to the n d dx. You cannot write this here on the end of it. It is not a multiplication. It is an operation, just like sine is an operation. You take the sine of something. Same thing with d dx. So when you look at this notation up here, it means take the derivative with respect to x. That's how to actually interpret that. We're going to do the proof. Now, there's a couple, technically this rule applies to many different powers, rationals, negatives, things like that. So we have to technically prove it for all of them. For right now, we're going to just prove it for the integer. I just want you to know that I did put down here a link. As we go along, as our skill level increases, we are going to prove the other parts of this as well. But if you're curious, they are here for rational exponents, and negative integers are here as well. But for now, we're going to start with n is an integer. That means it's going to look like a binomial expansion when I do this. So look, we have d dx of x to the n power. that is going to be the limit. I'm going to use h. You can use delta x, but h is just less messy. But you can use delta x. It just visually gets harder sometimes to visualize. We are going then to substitute in. It's going to be x plus h. H's kind of look like n's to the n power over x to the n. That's my f of x over h. And then you need to expand. So now we have it to the nth power. So we're going to use the idea that we had for the nth expansion before, because something neat really happens. We have h approaching 0, and then this whole expansion, so I'm going to make a long one here. It's going to be x to the n plus, I know it's going to be n times x to the n minus 1 times h. So I'm reducing the x's by 1 and then powers of 1, and the h's are going to increase by a power of 1 in each term, plus, and then the next term is going to be some constant, and it does not matter. I'm just going to call it sub 3 because it's the third term. That's it. Some constant x to the n minus 2, h to the second, plus a whole bunch of middle terms. And then we're going to get plus, and then we have same idea here, some constant. It's the third to last term. So it's going to be x squared h to the n minus 2. Oh, I need to make this longer. Plus the second to last term is the coefficient is n again. And then we have x h to the n minus 1 plus 1 is the coefficient for the last term, h to the nth power. That is the entire expansion. And then we have minus x to the n on the end here. And then all that over h. So look, just to highlight, the expansion, that one, is all of this, all of that mess right here. And then the second part of that, minus the x to the n, that's this one on the end. But we can do a little bit of cancellation here because the x to the n's cancel out. Now I notice in the numerator, every single term has at least one h. And as you see, you are increasing the number, the degree of each h in each term. So that means all the middle terms will also have like h to the third, h to the fourth, h to however high we go. So in other words, every single term has at least one h. All right, so let's then factor that h out. So we are here. Make a little more room here. So then we have the limit, which I haven't taken yet, h approaching 0, and then taking out the h. So the first term, that's this one here that I'm circling right now. That first term is then going to be n times x to the n minus 1 plus the second term then inside is going to be k sub 3 x to the n minus 2 times h plus, now the next term would have an h squared in it and h to the fourth in it and so forth until we get down here to the end, and I get k to the n sub n minus 3 x to the second, but don't forget we factored out an h, so this one becomes n minus 3 instead of n minus 2, plus the second to last term is n x h n minus 2, and then the very last term is going to be h to the n minus 1, all over h. Now the h's cancel out. So now we're left with everything just in the numerator. Now every term, I'm going to apply the limit as h approaches 0. So any term that remains that still has an h in it, for example, this one, all these middle terms in between will still have an h. This one has an h, this one has an h, this one has an h. All of those will approach 0. So what we end up with in the end is, now that I'm applying the limit, n times x to the n minus 1. And that's what we wanted to prove. We wanted to prove that d dx of, so the derivative with respect to x of x to the n is equal to n times x n minus 1. Now that's for all n's greater than 1 because you have expansion. So therefore that applies for that. If x was, the power was equal to 1, for the next one, it's done very similarly. By the way, that's called the identity function, f of x is equal to x. Not that it matters here. Let's see if the power rule still works. If I was going to do the power rule here, it would mean f prime of x would have to be, the power up here is 1. That becomes the coefficient. And then we get x times 1 minus 1, which is equal to 1 times x to the 0 power, which is just 1. So in theory, we should be getting a 1 if I do this to the x. So I have the limit as x approaches, no, not x, h, excuse me. Whoops. The limit, again, working offline, I know. The limit as h approaches 0 of substitute in x plus h minus x over h, which is going to give me the limit as h approaches 0 of x plus h minus x over h. The x's cancel out. And now we have h divided by h, which is 1. So the limit of 1 is just 1. So look, it agrees with the power rule.